In the delay 1000 function, 1000 stands for 1000 milliseconds. There's also a function called delay microseconds, where whatever value is in there is in microseconds. The difference between analog write and digital write is that analog write writes a pulse width modulation wave to a PWM pin. What that means the wave varies, whereas digital write can only write either a high or a low value, a 1 or a 0. The pins on the Arduino that can be used for the analog write function include D3, D5, D6, D9, D10, or D11. These are considered the PWM pins. The analog write function actually has nothing to do with the analog pins. The digital write function can use any of the digital pins. A call to analog write is on a scale of 0 to 255. This is the duty cycle between always off and always on. The PWM frequency of the Arduino is 490 on most of the PWM pins, but on pins D5 and D6, it is twice that as 980 Hz.
This is the blink program that is featured in the Arduino example code sections. We have a 330 ohm resistor and an LED light that blinks intermittently. This is hooked up to digital pin 13, which is what sources the code. This is the blink faster function, where I have created a delay length and I have set it to 50 milliseconds. This is actually a little bit difficult to record as my computer camera cannot register this frequency. The highest frequency that the average human eye can register is about 80 Hz. If you convert that to milliseconds like I did, that is 12.5 milliseconds. So I'm going to plug that in as my value for delay length. And we can now see that it appears, at least from the camera, that the LED is no longer flashing. In actuality, with my own eyes, I can see it flickered. However, when I make the delay length value 10 milliseconds, it registers as always being on through my eyes. This is the fade code as it appears with the LED. I currently have the duty cycle set to 60. Now let's compare this with 0. As we can see, the time it takes for this to fade is much shorter than it had been. Let's set this to the maximum value of 255. The fade occurs rapidly now. Almost looks like our previous blink function. So for my manual fade function, I used digital write commands instead of analog write commands to get the LED to dim and brighten as it had done previously. In order to do this, I used a series of for loops. In these for loops, the I value is the duty cycle. I have the I value set to 2, which makes it go fast. If I were to set this to 5, now that I have set it to 5, the program will run at a medium speed. If I set this to 10, or truthfully anything higher, it will go to a slow speed.
An advantage of the manual PWM cycle is that a duty cycle can be much more precisely chosen. A disadvantage, however, is that the program doesn't actually have a set level for brightness.
Now the two delays that I have in the for loops are always functions that will sum to 2 milliseconds. This is so that the code maintains the 2 millisecond pulse width modulation period that we saw in the analog write period. So for example, my delays are set to one value minus 10 of itself, and the other value is 2000 minus the previous one. This way, they always coincide to sum to 2000 at every point in time, and we can simulate pulse width modulation using the digital write feature. So for the final creative part of the project, I hooked up an AND gate to the breadboard. As you can see, I've also added additional LED at the bottom left and up top. This LED on the bottom left uses an analog write command to fade it in and out. The LED on the bottom right uses the digital write fade command that I wrote in the previous problem. They are hooked into an AND gate where they're each inputs, and the output will illuminate this LED. To show you how the AND gate works in conjunction with this, I've disassembled it and made it so both of these LEDs are lit. So what you're seeing happening is the digital write LED is going through its cycle fairly quickly. Every time it completes one step in its cycle, the analog write LED on the left enters its next step, so it has gradually gotten brighter. The reason it works like this is because they're both used in the void loop, so in order for the analog write LED to move on to the next phase, the digital write LED has to complete a cycle. When both of these are hooked up to the AND gate, we saw how it affects the final LED.